So hello, everyone. My name is Nikhil Barthwal, and I'll be talking about implementing event-driven microservices architecture in functional languages. And I'll cover some basics of microservices and event-driven microservices. Microservices is fairly common, so I guess most of you would know what microservices are at this point of time, but I have some material just because I want for the sake of completeness. As mentioned before, my code examples are in F#, but the concepts are basically language neutral. So if you are from Haskell, OCaml, Scala, or any other functional language, you still will be able to use most of what I'm saying, and probably not the code examples I said unless you translate them, but pretty much concepts would all be applicable there. All right, so let's get started. So what are my two objectives with this talk? The first one is to convince you why functional paradigm is a great for implementing event-driven microservices. So that's objective number one. And the second objective that I have is how would you implement them using programming language constructs? Now, functional programming, has its own unique programming language concepts, and I want to cover how would you translate ideas of distributed systems in functional programming language constructs. All right, so we'll start with the basics. So Monolith, right? The good old approach. You have a single service. There are a lot of benefits to Monolith. Simple database, you have a persistence layer, and then you have multiple clients talking to web service. Obviously, this is a simplified diagram. In real life, you might have multiple replicas and, a load balancer, et cetera, But conceptually, the concept you have is that rather than having an assembly of service, you have one big service that does everything. And there are a lot of advantages. It's a simple system. It's very easy to develop, test, and deploy, but it doesn't scale. And it doesn't scale for several reasons. So, for example, when you have a large code base, right, then it slows down the development because, you have to compile, you have to test. There's a huge array of tests. So it's not really very scalable. It'll slow the developer down when you have a big service. You would need more time to test and deploy these services because they are big, so it takes more time. And worst of all, you have too much of team interdependencies because you have several people working on the same service from several teams. Every time you make a change, it will affect everybody else, right? And every time what happens is you want to make a change and you're ready to deploy, but the other team is not ready, so you'll have to wait. So because of all of these team interdependencies, you really cannot ship the product very fast. So that's a huge drawback of the monolith, which is something that the microservices solve for you. So what are microservices? Microservices are small autonomous services, right? So instead of having one big service, you basically divide your problem into smaller services that act in a single autonomous from each other, that act with a single purpose in mind, and together they deliver the same functionality that a monolith would do, right? So it's basically an approach where your application is divided into a set of small services. And typically, these microservices communicate with lightweight mechanisms. What are lightweight mechanisms? Lightweight mechanisms are something like REST calls or gRPC and so on. Essentially, they are technology agnostic communication mechanism. And the reason why they are technology agnostic is, by definition, although in practice it's actually not that true, by definition, you can have these services implemented in different languages. So you could have some services in Python, you could have some services in Scala, you can have some services in Java, etc. And they all have to communicate with each other. When they're communicating over HTTP, REST, or through a message bus and so on, then it doesn't really matter what technology you're using to implement that service. And that gives people a lot of freedom to pick the right tool for the right problem. So that's another big advantage that microservice has. So there are some references for microservices. Microservices itself is a very big topic. You can have an entire conference on microservice. So obviously, I'm not going to cover that, but I have some good references for what microservices are in case you want to go deep. So what are the advantages of microservices? Well, to start with, we looked at the monolith and we realized that there was a lot of team interdependency, right? With independent services, what you get is independent deployment, independent realizability, right? I don't have to wait for the other person to deploy my changes. So it gives you better, faster time to innovate and better scaling also. Why is it better scaling? The reason why it is better scaling is because when you have one big service, and let's say you have a lot of load, you scale that service, but you're scaling the entire service, not every part of the service. Let me just check. I'll cover the disadvantage also. Okay. Yeah. When you have how do I minimize it? Let's just keep it like that. Aside. Yeah. So when you have these different services, you can scale the parts that are overloaded. And that way you actually can scale certain parts and not scale certain parts that are not overloaded, and that gives you better scaling capability. We have already looked into technology heterogeneity in the sense that you can have multiple technologies to implement these services. And then you have resilience. Why do you have resilience? Imagine that you have a bug or something crashes in your microservice, in your service. In a monolith, if something crashes, the service is down. The entire service is down. There's no concept of partial failure. Either you're working or you're not working. Whereas in a microservices, if a particular service is down, it doesn't mean the entire system is down. It's just that one service is down. So system can still operate. For example, imagine that you're in Amazon or Netflix, right? And the recommendation services goes down. So every time you log in, there is a section on recommended products based on your prior purchase history. You won't see those kinds of recommendations, but the system still will operate. So that is why you have more resilience. Ease of migration. Technology stack is rewritten every couple of years. And when you have a monolith architecture, when you're migrating, you basically have to migrate the entire service, right? You have to rewrite the entire service. And if it's a big service, it's really painful to write that entire service. With microservice, what you have is you have these individual services, so you can migrate them one by one. Let's say you were using Python and now you want to move to Golang, right? You don't have to do it all at once. You can just take one service, migrate it to Golang, and one by one, over a period of time, you can migrate the technology. So ease of migration is a very big factor because, systems outlast the programmers. Basically, people will move on, people will change jobs, you would lose all the domain knowledge. And at a future point of time, your technology will get obsolete and you would need to migrate. So that's one big advantage microservices has. Let's actually pause and let me just cover some of the questions you have. What are the main disadvantages for using microservices? When do you not recommend that strategy? Okay. So the main disadvantage that you have with microservice is that when your system consists of a lot of moving parts, the chances that things will break is going to be high, right? So that's one disadvantage. System is brittle. So you can fix it easily. You can operate under partial failure, but chances that things can break is going to be really high because you can have one service call another service and something happens there. You could have the same thing in monolith also, but monolith chances are less because you have less moving parts. The second disadvantage that you have with microservice is that you need a lot of automation. When you have a monolith, you don't really need a lot of automation in the sense that you have one service. You could have an entire deployment pipeline just manual. It doesn't really matter. But when you have like 1,000 microservices, you can't really deploy 1,000 microservices individually. You would need some kind of automation. So there has to be a lot of investment done in DevOps, automation, all those tooling, CI/CD, when you're using microservices. Okay. Can microservices utilize lower level communication for communication like UDP to improve response time and reduce latency? Well, obviously they can. The question is, should they? The answer obviously depends on the problem you're going to solve. Now, understand with microservices, not every service needs a high latency, not every service needs, needs reduced latency, not every service needs high response time. Typically, you have different services servicing different concepts. So you can try to use low-level communicatives like UDP for certain services, but not for everyone. There was one point I forgot to mention about when do you not recommend such a strategy. When you're bootstrapping a system, it's almost good to use a monolith. A monolith is a great starting point for a system. It probably might not be a great ending point, but it's a great starting point. Another case is that when your services don't change frequently. See, one of the big advantages that Microsoft Services has is it seems no info at presentation page. I'm not sure what that question is. That is something that Dania would have to look. It seems no information.
We see just the name. Yeah. So now we see. We saw
okay.
just the name of the slide.
Okay. Yeah. Okay. Good. Awesome. Yeah. So, sorry, where was I? Yeah. So monolith is a great starting point. Also, in a case where you don't really have a lot of changes or your rate of velocity of features is very low, you might as well stay monolith, because even if there is a lot of team interdependency, you don't really need to ship the products really fast. There was a huge case study that Amazon Prime, basically they moved to microservices, and then they realized that this is not good, and then they moved back to monolith, and they was famous, and they saved I don't know how many resources. Now I don't know specifically what was the use case, but sounds like, you know, if you don't deliver a lot of features, you might as well keep monolith, because the disadvantages of Microsoft are still huge, right? You have a lot of these services, brittle, everything. And the real advantage you're getting is faster shipment of features. But if that's not what you want, then there's really not much benefit of using microservices. Data consistencies in microservices is a big problem. Yes, and I have a whole section devoted to that. So I'll answer your question about data consistency when we get to that page. What instruments of communication between microservices do you think are more stable and useful? I'm not sure what you mean by what instruments of communication. I mean, you're talking about how microservices communicate. Typically, for testing purpose, okay. We'll talk about testing in a while, so I'll cover that question there. But regarding communication, typically, and I'll cover communication in greater details towards in the middle of the presentation, but typically there is obviously request response type pattern, which you use REST. You could use message bus, which is much more scalable, but async. Both these are covered in details in the later in the section. What are the criteria for good microservice? So the principle behind microservices is single responsibility principle, right? A microservice should be doing one thing and one thing really well. That's the criteria of good service. Now, what is a how do you differentiate whether the service is a microservice or a monolith? This is more of an art than a science. There's no really scientific answer to this question. Typically, empirically, microservice is a service that you can write in 1 or 2 weeks. That's basically what you would call as a microservice. But thing is there really any hard criteria about this is a microservice? There is no such microservice. It's more intuitive. People generally have an intuitive notion of big and small, and you can use the same notion for microservice. When should I stop splitting monolith on a microservices? Okay, it's a much more intricate answer. The question is, first of all, understand what microservices are offering. Now, if the empirical rules are that if you are not going to change a service frequently, don't worry about microservices, right? Secondly, we talked about independent realizability and better scaling. If you think that certain part of the system is going to be overloaded quite a lot, whereas the rest, like, you know, the 80-20 rule, if you have 1,000 services, it's really those 200 services that are going to be used the most. The 800 are not going to be used. So what you could do is the ones that are not going to be used, you can keep them in a monolith. You also have to look at how your organization is structured, because remember, you have to basically, the Convoy's law, right? Communication pattern in an organization reflects the architecture. You need microservices would offer you an advantage that you have independent, how do I say? The teams are independent. So you can also split the service based on how the teams are structured, right? Let one team own one service or couple of services. You can use these golden principles. There's really no hard principle, but generally, it's a moderation is really good. There are some extreme cases where Uber had like 7,000 microservices, and then they realized this is too many microservices, and they started joining them. So you don't want to go on the extreme side, split everything you can. You have a clear advantage. I need this service because I think this is a single responsibility principle. This service should do this thing. I don't want to mix two functionality in one service. So that's the reason for the services to have two different services. You also want, like, I want teams to be independent. So that's a good reason for split. If you don't have any of these criteria, you could just continue using monolith, or basically not split the service that you intend to split. Okay. So microservices. So we have talked about microservices. Now I'm actually going to switch a little bit about functional programming. So I want to see what microservices is from a functional programming point of view. Okay. So functional programming point of view, think of microservice as a function, fx. And what happens with most of the services is, especially the stateless service, that you really don't have any dependency on an external state. So you can think of a service as a pure function. Okay. So pure services, that's how majority of your services are going to be. There is no side effect except logging. Logging is not something that we consider as a side effect in this context, although if you use some programming language like Haskell, logging will be a side effect because you're writing IO, doing IO to the system. The reason why in this context we don't really consider logging as a side effect is because logging is just not modifying the state of the system, right? It is just splitting out the state, but it's not modifying the state of the system. So that is why I don't really consider logging as a side effect. So I'll just say that any service that does not have any IO except logging is a pure service, and that's how you can represent them, right? Y is equal to fx. On the other hand, you also have services that modify the state, which is your persistence layer, right? And we'll see the layered architecture later on of how it works. But so this is the layered architecture where you have the service fx is equal to y, and then you have the input and the output state, right? So you can think of your microservice as a functional representation where a microservice would take basically an input and an input state and then split out the output and the output state. And this is really useful when you think of services from a functional programming point of view. Okay. So this is where this is what an impure service is. So you'll have side effects like IO to DB, etc. Not IO to logging, right? We have already talked about logging. That's not considered as a side effect in this context. So why do we not want to use object-oriented programming? The reason why we don't really use object-oriented programming is object-oriented programming is not a very well-suited paradigm to modify to basically be used in distributed systems. So object-oriented programming models the application as states, the object with states, but most of the microservices don't really have states, right? So really, why would you use object-oriented programming? Imperative, from where the object-oriented was designed, was basically for von Neumann style hardware, right? Where you have the state and then you have the machine that would read from the state, the original 1940 architecture. But microservices basically are hosted predominantly on the cloud or even in your private data center. They don't actually interact with hardware directly. And OOP, now another advantage that OOP languages give you is like Java, C# have a very good ecosystem. However, languages like F# Scala and now Kotlin can seamlessly interoperate with C# and Java. So you can take advantage of all of those libraries that Java or C# would provide you. So the interesting thing about it is, why do people use object-oriented programming? And the answer is, it's a little bit more historical than actually logical. You had the standard languages like C, Fortran, way back in 60s, 70s, and then they were hard to scale. They weren't able to design big systems. Object-oriented programming came with C++ and later on with Java, right? And it became the de facto standard. And then it was like, if you want to program, that's how you program. So it just becomes a way of programming, and it became popular. And now it's going to be used for everything, even in cases where it's not the best tool. Functional programming languages kind of appeared late, although that statement is technically not true, because the world's second most programming language, Lisp, is Lisp, which is a functional programming language, but they never really entered the mainstream till very late. And they really didn't had very good ecosystem. They were mostly thought of as an academic languages, more for researchers than for actual practical industry use. And that's why they were never taken very seriously for a very long time. Ironically, object-oriented programming has its roots in biology. Okay, and the reason is that one of the pioneers of object-oriented programming was a microbiologist by training. I forgot his name, but Alan Kay, yes. And I think he was behind Smalltalk or something. C++ was derived from Smalltalk. And I think Alan Kay was basically one of the Smalltalk designers, although I could be wrong here. And Alan Kay modeled object-oriented programming based on human body. So when you look at human body, our body is made of cells, right? And cells, basically individual cells that do one thing and one thing really well, and cell interacts with other cells through cell walls. And then you have the mitochondria, or the nucleus of the cell, which is like a state. So it's like, we can consider a system, any kind of system, like a human, where it consists of these cells or these objects. And what about these objects? What they have is they have an internal state of this object, which is their private variables, right? Private variables, which is not visible to external. An external entity, when it wants to manipulate the state, has to call the public interface or public functions, or whatever you call it, public methods, to basically modify the state. So this is how object-oriented programming came from microbiology into computer systems. And now we, in a way, have extended it to microservices, because when you really think about microservices, essentially microservices is nothing but a application of object-oriented programming into distributed systems, in the sense that each service has its own database. And we'll talk about how each service having its own database. Each service has its own database, and that's like a private state that you cannot access directly. And what you have is, you have these services that would interact from the service. The service will actually be your interface. The service exposes a contract, and you would just interact with that contract, and that would manipulate the internal state. So that is how this whole microservice is basically nothing but an application of object-oriented programming to the world of distributed systems. I see some questions. Database by itself is not a part of any microservice, but exists like an independent service accessible by, no, that's not the case. It's actually in a microservice architecture. I'll explain this question in details later on, but in a microservice architecture, database is attached to a microservice. You could have more than one databases to a microservices, although in reality, you only have one database to microservices. It's not accessible. It's not an independent service that can be accessible by any microservice. That's not how it's done. How about Erlang? I'm not super familiar with Erlang, so I don't really know. I don't know if I can answer that question, but do you have a specific question about Erlang? What about Erlang? DB aside, sharing DB by multiple services is an anti-pattern. So a microservice with a DB is called stateful. So yes, sharing multiple DBs is an anti-pattern. And the reason why it is anti-pattern is because one of the advantages that microservices have is independence from each other. Now, the moment you share the loose coupling architecture, which we'll talk later on. The moment you share DB, you have increased the coupling and you have introduced the dependency between services, which kind of defeats the purpose of having a microservice architecture in the first place. Microservices with the DB is called stateful, yet it is, and that is the reason why I have used the word mostly. So if you have a microservice architecture with, let's say, 1,000 microservices, some of them, typically 10-15% of them, will have a DB. So yes, they are stateful services, but the 80-85% do not have it. And this is the reason why I'm making the statement microservices mostly don't have states. I'm not saying microservices don't have states. They do have states. Not all of them have states. And I'll go back to my previous slide, and this is what I'm talking about. Sorry, I think I went too far ahead. Let's go back. This is where I'm going to talk about. This is the microservices with a state. So this is what you're mentioning, that I'd say about 80-85% of them are pure microservices, which is one on the left side, and about 15-20% of them are impure services. They are the ones with state. Okay. So moving forward, we have talked about this. So let's talk about how would we model a service architecture in functional programming. We saw how you can model a service as a function. Okay, so how you can model service as a function. Then you're talking about events. We are talking about events modeling, right? So you have algebraic data types. Algebraic data types in Scala, I think, is case classes, is what they call it. And F# people, they call it discriminated unions. But you have these events, and we'll explain what these events are, etc., in greater details, but you have these events that trigger these services. So how do you model these events? You model these events using algebraic data types, case classes or discriminated unions for Scala or F# people. Service we saw is a function, and then events are mutable. So events basically represents a change of system at that one point of time. You can't go back in time and change something. So events are fundamentally immutable by nature, and we know that functional programming is basically pure functional programming has immutability, although most functional programming languages allow you to add like F#, Scala will allow you to have controlled impurity from time to time. And then again, mostly stateless services means predominantly pure code. Mind you, pure code will include logging. We have covered that part. So mostly the services are stateless. So mostly functional programming says that you should have pure code. And if you have impure code, one with an IO, you should probably keep that separately. That's how a good practice is. If you use language like Haskell, then you don't really have, you already have it in the sense that the code is pure and impure code is kept separate by IO monads. So the key idea is that functional programming is basically capturing the behavior of a service architecture very naturally, because when you're looking at what is happening on the service world, and then you look at what is happening in the functional programming world, you see that these are actually almost a one-on-one translation of concepts. And this is the reason why I'm making the statement that functional programming is a very, very good way to implement services. So here's an example of implementation. Now this example is an F#. You would define an input type, right? So imagine that you want to do some e-commerce. So you have an item SKU, you define an output type. So this is what my input is. This is what my output is, right? You have an inventory, it's not in inventory, you have an expected date, or I don't sell this item, this is my item. And then all you have to do is write a function that basically converts input to output. So in object-oriented programming, you have that concept of object-oriented analysis, right? Where you basically take your problem and essentially you just write classes, but you're just writing the interface for the classes, right? So if you're using C++, just write the header files. If you're using Java, don't worry about implementing, just write all the interfaces for the classes, right? And then that's your system architecture. And then you go about implementing one by one those methods inside, right? So functional programming kind of does the same thing in the sense that you have these events. So you model these events using the algebraic data types, which is case classes for Scala or discriminated unions for F#. You define all of these types, and then you just write these functions that convert from one type to another type. And that's how you go about implementing these services. Okay, so this is about functional programming now. We have talked a little bit about interdependency. Now we'll cover a little more. So each microservice is supposed to have one database, or it can have more than one databases, but you never, it's an anti-pattern, you never share a database across two services. And when I say each database, it could be a physically a different database, it could be a logical partition. It doesn't really matter. You could have a case where there's only one database, but it's logically partitioned into multiple tables, and each table is owned by one service. That's okay. The key thing is that table schema should not be shared across multiple services. You could have one physical database, but individual tables should not be shared. And the reason is that the very nature of microservices is that services should be loosely coupled, right? You should not have architectural coupling between the two services. Now, the moment you share the schema of the table, you have broken that coupling. So imagine if one service basically wants to change the schema and add something else, you can do that, but if you're sharing that schema with another service, you break another service. And that's going to be a problem. So that is the reason why services do not share schema. You could have multiple databases attached to one service. That's okay, but you can't have multiple services attached to one database. Here, what kind of happens is that services basically expose a contract, right? So this is my public interface. The same thing as you're writing C++ or Java, you have the public interface of a class, right? You can do anything on the private methods, add and subtract methods. It does not really matter. So the only thing that matters to others is when you change your public interface. So in microservices, you basically have this public contracts that you share with other services that services are supposed to use. You can do whatever modifications you can do internally, nobody cares. But when you're going to change the contract, that's where you have to get in sync. And that is where there is going to be a dependency across multiple teams. But the idea is that most of the time, there will not be too much of contract sharing. In fact, we can go about saying that you can have multiple versions of contract. You could see from REST API that you can add more endpoints to a contract. That's okay. That's not breaking the backward compatibility. But the moment you want to change, typically what you do is you version the API. So you have V1 of that, V2 of that. Versioning is a whole different, like, it's a whole different area that I won't go too much into it. But essentially, the contracts, if you have to make a fundamentally different contracts, fundamentally different, like you have to change that interface in a fundamental manner, what you should do is you should create a different V2 version or V3 version of your API and let your services use V3. And over a period of time, your expectation is that everybody will use V3 or your latest version, and then you can start deprecating. Otherwise, you can even change the contract, but then you have to get in sync with multiple services. But it should not happen frequently. It should be rare for you to do that. So you have a database per service. And what that means is when you have loosely coupled services, right, it reduces the team interdependencies. And that means you can deliver the features fast, right? So faster innovation to your customers. And we have a question. Microservices have many moving parts, including microservices with their own database schema. How do you ensure that database has all the necessary tables for such microservices, especially for new microservice? Okay. That is a good question, and that's actually related a little bit to database consistency. So I'm going to answer that question in a little while because I have a section devoted to this part, right? So once we get to that point, we would answer that question, but let's move on. Contract management. Okay, so we have talked a little bit about contract management. How do you manage contract? More specifically for F#, F# has F# type providers. This is basically, you can give a sample that this is what my input output. Typically, services will exchange JSON snippets or XML snippets, mostly JSON or YAML snippets. So F# has type providers that can capture and create your basically data type for it. So, you can define your contracts as snippets of XML JSON store them in common locations, because you have to store them in common locations because services would be sharing the contract with each other, right? Contracts are how services communicate with each other. So the contract is exposed to other services, inner details are not, and then you can store them in some shared location. Say you have a mono repo where different services are in different folders, you have some shared location where all the contracts are stored, and then you can have the code reference them. You have other options also. You have, Apache Thrift and Google Protobuf in case you want to use some binary mechanisms. Contract management's typically, like I mentioned, a good idea for contract management is versioning. So you should basically version them, and it's always a good idea that all your schemas have versions on them. Okay. So now an important question that comes to mind is, we are talking about all of this assembly of services, etc., but how do we divide these services, right? How do we divide this functionality? And this is where domain-driven design would come into the picture. So again, I'm not going to go into details of domain-driven design because domain-driven design itself is a big topic, but I'll just cover very briefly what domain design is and how it's going to be used for microservices, okay? So domain-driven design is basically an approach to software development where what you have is you think of your software as an evolving model, and your implementation is essentially managing that evolving model. So there are it's loosely related to model-driven architecture where you basically think of your software as a model, and you have these building blocks. So what are these building blocks for domain-driven design? You have bounded context, you have entities, you have value objects, aggregates, and services, right? Bounded contexts are basically distinct domains. Entities are actually the entities that make up. Value objects are immutable objects which have some functions attached to it. Aggregates are basically things that you take into account together, and then you obviously have the service. There are some excellent references for domain-driven design. I have included that. Like I said, domain-driven design itself is a big topic, and I won't go into details of it. We would cover aggregates for the scope of this talk. We'll just talk about aggregates because I think aggregates is the one that will actually be useful in dividing the functionality. How do we synchronize data between databases? Yes, I'll answer that question towards the end. There are specific patterns that do that. I'll answer that question at that point. Okay, so what are aggregates? Aggregates are essentially cluster of domain objects that can be treated as a single unit. And typically they have a root from where you can reference that. For example, let's say you place an order for Amazon and you order some box of chocolate, some gift, something. You have a big order. This order has an order ID, and this order is a single unit, although it consists of multiple items in it. So you can treat this order as a single unit, and it has a root, and you reference that order from that order ID. So that's an example of aggregates. And then your domain model is essentially a collection of aggregates. You could also say it's a collection of bounded concepts, but it's actually a collection of aggregates. So your domain model is collection of aggregates. And then what you do is, I am having a hard time with moving this window around here. Let me just get it out of the way. Yeah. Then what you do is each aggregate can be a separate service in itself. So here you have order service, you have customer service, you have product service. Aggregates would provide you the boundaries for partitioning. So how do you partition we have talked about assembly of services. We know that whatever functionality we want to deliver, it has to be basically split up in different services. How do we partition them? So aggregates are the ones that are actually going to give you the boundaries for that partition. Now, here I should mention that there is no unique way of partitioning. For example, if I look at this diagram and I've split order, customer, and product, I could have order service and product service as one service and customer service as separate service, right? There's nothing wrong with it. There's no unique one-on-one that says products have to be separate from orders. So you can split your system as fine-grained as possible. You can split your system coarse. That is more dependent on the problem that you're trying to solve. Remember, each one of the system gets translated, subsystem gets translated into a service. So now the question is, how do you want to split the service? And we have already talked about the criteria for splitting or not splitting. Again, if you don't want to have a frequent change, then you basically don't want to split the service too little. Again, if it's like Conway's law and how your team is structured, that is how you want to mirror those services. So your actual splitting will take all that factors into account. But basically, aggregates are the boundaries from where you can split those services. Okay. So this is the reason why this is the application of domain-driven design in the world of microservices. And what domain-driven design basically does is it has architecture. So it has the infrastructure layer at the bottom, which is where all the services with your pure database would be. You have the user interface, which is basically client interface running on your mobile app or client browser. And then you have application and domain. Domain is where most of your code is going to be. And what DDD advocates is domain layer, which has the bulk of layer, basically are value objects, and they can be modeled by F-sharp's discriminated unions or Scala's case classes, and they have attached member functions. So you can basically do something, or you can get some value or whatever. So they are not anemic domain models. Anemic domain models is basically a concept we use where domain knowledge is nothing but a collection of data. If it has functions attached to it, then it's not an anemic domain model. So you have these DDD architecture layers. And we saw that functional programming in general, F-sharp Scala in particular, would be really handy here in implementing the domain layer, which is where most of your code would basically reside. Okay. And these can be treated as an executable specification because you basically have these functions defined in some form of schema, right? That when you compile, they can be checked. And this eliminates what we call as a model code gap, because what happens with all these modeled approaches is people write these contracts in form of some documentation, and then they implement, and over the period of time, document goes in one direction and code goes in another direction. At some point of time in future, you realize that what the document is claiming and what the code is are two different things, right? They're not in sync with each other, and this is the model code gap. One of the big advantages with all of these algebraic data types definitions like discriminated union or case classes is that you actually can write specifications which are executable. So if you make a change and it's incompatible, the code breaks. So it can be checked at compile time. I know this question has been asked a lot of times about distributed data. So how do we keep the data consistent? And how do we query scattered data? So that's a big problem with microservices. Could you give some practical example of aggregate service used on production? And next, how do I solve common concerns like caching, user sessions, or complex expensive objects built by one service and used by another, invalidating those stores in auto-scaled services, gracefully failing them? Okay, so let me first go back and answer the first one. I mentioned that, but let's say you're designing an e-commerce system like Amazon. So we have talked about order, right? Order management is an aggregate. That can be service. We have talked about products. Each product has an item name, item number, inventory. That's another aggregate, right? You refer to each product has an ID, but it has several fields. So that's where. So if you look at this diagram, this diagram, in a way, is answering your question. And this is an example of how aggregate services used in production. You have these three different services modeling three different aggregates. Okay. Now, how do I solve common concerns like caching or user sessions, complex objects built by one service, also used by another, invalidating them? Those ones, you actually model them in the application layer. So let's actually go back to this diagram, and you see this application layer. Application layer is the ones that has nothing to do with domain layer. That would model that. Application layers kind of can be impure. I mean, it kind of depends on your programming language. It's not really, when you have all of this, cache basically is going to break your modeling. Caching is actually kind of very simple because caching sits in infrastructure layer in a way. User section and all those things are objects that are built by use, but these objects are basically in a way a binary objects, right? They are not really data objects. So there you probably will use some kind of binary method, like, and then you can use protobuf, etc. Or you can have some tokens that are basically captured in your ADT. Obviously, when you have invalidating them through stores across and all those things, you're kind of breaking the immutability aspect of it, but you just have to do it in a controlled manner. This is actually a very problem-specific question. So I don't know how I'm going to fit it in the grand scheme of things. Your programming languages, mostly F# Scala, do allow you to do impure codes. So there's nothing stopping you from doing that. You just have to be careful in how you do it because you're introducing an impurity in your system and you want to do it in a controlled way. That's what I could say. Okay, let's actually go back to the problems with distributed data. Now, we have two major problems when you have one, how do we keep the data consistent? For example, we placed an order, we bought some products. Now we want to make sure that the product database is consistent in the sense the inventory count gets reduced. So we want to have the consistency. And secondly, we have to query scattered data. So one example of query, I think I have it in the very next slide, is this is an example of a SQL transaction, but you can't really easily do it in a microservice architecture because customers are private to customer service, products are private to product service. So you can't really use ACID transactions. So how do you solve that problem? You can't even use two-phase commits because it guarantees the consistency, but two-phase commits are really very impractical to use because they are very chatty. For one, they are single point of failure. They are chatty because the complexity is too high. And also, when you have a lot of locks, you are decreasing the throughputs, and these services have to be highly available, have to have very high throughput. So you can't really use two-phase summits. There are ways in which you can use them. We have the CAP theorem. For those who don't know what CAP theorem is, it says consistency, availability, and network partition are three aspects, and you can't really have all three of them simultaneously. You can only have two of them simultaneously. So if you use two-phase commits, it will make your service less available, and availability matters because imagine service like Amazon crashes for 1 second, just for 1 second, think of how much revenue they would lose. So availability matters there. So here we are going to use the concept of eventual consistency. So we know, and I've already briefly mentioned, we know that you can't have all three of them together. So CAP theorem, right? So what we're going to do is we're going to replace consistency with eventual consistency, and we're going to switch to event-driven architecture, and I'll explain in detail what that is. Event-driven architecture uses a concept of eventual consistency, which means the system is not consistent right away, but given a period of time, it will eventually reach consistency. And a period of time typically is very small, few milliseconds or maybe a few seconds. So it's not like you have to wait a lot. So given a period of time, you would use eventual, it will become consistent. This is called as eventual consistency or weak consistency or whatever you call it. And this is where we use event-driven microservice architecture. Event-driven microservice architecture, often people think are one and the same thing, but they're actually not one and the same thing. Microservice is a general term, and event-driven microservice is a specific architecture that uses events. I know we have talked about events in events modeling, and now we're going to talk a little more about what these events are, how we model them. So event-driven architecture basically says that event is whenever there's a change in the system. So whenever there's a change in the system, that event occurs, that event is then broadcasted through a channel, and all the listeners get notified, and some listeners would take action and some won't. And typically this happens asynchronously, right? So it's a highly coupled, highly distributed, loosely coupled architecture. What that means is the person who broadcasts these events may not know who the listener is, right? He's not aware of it, and new listeners can come and go. It doesn't matter to the broadcaster. So it's a very distributed but loosely coupled architecture. And it's used for asynchronous flow of work on information. In fact, when you look at event-driven architecture, you use event-driven architecture or such kind of architectures in everyday life. An example of event-driven architecture is airports, right? An event happens. A flight is about to depart, a flight is about to close the date, a flight is delayed. This is an event, right? A change in the state. A notifier will broadcast it. This is what is happening. There are passengers on the airport. Everybody would listen. The notifier does not know who are the passengers. He doesn't know how many passengers come and go, right? He doesn't know. He just makes an open broadcast. Some of those passengers would take action. For example, if the notifier says announcement is being made, flight door is being closed, people who are on this flight, please rush to the door. People who are on that flight will take actions, and those who are not will just ignore it. So that's an example. It's a very practical example of event-driven architecture, basically, that we use in everyday life. So that's what event-driven architecture is. And then in event-driven architecture, you also have an architectural pattern called event sourcing. And what is event sourcing? What event sourcing says is that don't maintain the state of the system as a final state, but maintain the state of the system as a sequence of events. So when you have these events, you can combine these events, play them forward, and the system state can be generated. So you basically store the events, and then the advantage, you store these events, and then you combine these events, and you get a total state of the system. And the advantage it gives you is it enables you to go back in time, and you know how the system is evolving in time. It also allows you to create new workflows because you can combine and recombine these events in a way to create new use cases that you hadn't thought about initially. In fact, talking about event-driven architecture in event sourcing, this isn't a new idea. We have been doing it for ages. For example, bank ledger, right? When you go to a bank and you open up an account, your bank has zero balance, right? There's no balance. Then you deposit or withdraw money. So that's an event. And what is the state of your system? The state of the system is total money that you have in your account. What is that state? Nothing but the sum of all the transactions you have done. So every time I deposit, that's a positive number. And every time I withdraw, that's a negative. And if I add all of these transactions together, then I get the final state of my system. So that's event sourcing. A bank not only stores the final, in fact, it doesn't really store the final balance as such, but it stores all the transactions. And then you can go back in time and you can see how I'm doing with my finances. You can actually go back and, if you use credit card and there are some fraud that happened with your credit card, you can go back in time, you can take that transaction out, and then you can replay all that transaction forward. And that's a good example of you can combine and recombine these events to provide a workflow that hasn't, to provide a state that hasn't been thought before, right? By enabling you to store all of these transactions, you can actually roll back. You can go back in time and you can combine and recombine these events. Another example of event sourcing is version control, Git. Every time you check in, what do? Your state of the system is your source code, okay? Every time you check in, you're storing the deltas. So you store these deltas of transaction. Every commit is basically a delta, and your state of the system is nothing but a sum total of all the commits that you have done over a period of time. Okay, so that's your state of the system. Version control is another example of event sourcing. Essentially, in distributed systems, we have these fancy names, CQRS, event sourcing, etc., but when you really look at it in real life, in one form or another, we are very familiar with that, and we have been using it for ages. At least banks, we have been using it for ages. So how do we implement event sourcing in a functional language like F#? Well, very simple. You have these events F1, F2, and all you have to do is fold. So fold function, and I think Scala has also something similar, list fold function, basically can take these events and just fold them together to get the final state. And you have an initial state where in Git, it'll just like a blank, empty repository. In a bank, it's an account with zero balance, and you just fast forward. The only problem is that if you have to build the state of the system from the beginning, it can take time because you can have millions and millions of events. So a real life optimization is that you replace this. Actually, slide is light of misleading. You replace the initial state with a snapshot state. This arrow should be on the initial state. So you replace the initial state with a snapshot state, and then you can use snapshot for performance optimization. For example, in bank, what you have is bank calculates and caches the end of day balance for you, closing balance for the day, right? So let's say you want to know the balance at 11 o'clock today morning. The bank will say, okay, fine, let me calculate his balance, but it's not going to calculate from all the beginning of when you stored the account. It will actually use the most recent snapshot that it has, which is basically the end of the balance for yesterday, and this replay the events. So you basically use snapshots here. And with snapshots, you can actually do an optimization. So you don't really have to replay all the events, and then you can just store the snapshots. So what are the benefits of event sourcing, and obviously the drawbacks of it? Benefits, you have a very accurate logging. We saw that you can go back in time and I'll answer your question. Yeah. You have a very accurate logging. You can have temporal queries, right? You can look at it at some point of time, what my queries are. And one of the things that you can do is applications can process the same events, but create different views. We'll talk about views when we talk about CQRS, but think of it that you're implementing a social network like Facebook, okay? So you have a Facebook page and you have 3 main sections, hypothetically. I think I've covered that example a little later. And you have these events that are happening, right? Like you went on a vacation, you posted a photograph. These are all events that are happening, a change of your state. And how these system processes that each one of these subsystems, they take the same events and then they create a different view. I'll cover this example in greater details in the next slide, I think. But we'll talk a little bit about the drawbacks, and then I'll answer some questions also. It adds complexity, obviously. There's a lot of complexity that you're adding. You don't have strict consistency. Sometimes you need it, but most of the time you don't need it. So you don't have strict consistency with events because it'll take time for events to basically be replayed, stored in a system. Events will travel through a message bus, so you don't really have strict consistency. You have longer boot up times. We talked about that in order to create the state of the system, you have to replay that events, although we can use snapshot that will greatly optimize, but you have longer boot time. Okay. So now let me cover the example of applications can process the same events, but create different views. So let's look at an example of Facebook. In Facebook, what you have is, let's say you have a timeline. Let's say you have 3 components. You have a section on your personal info, you have a photo section, and then you have a timeline. Events happen. You went on a vacation, you posted some photographs. Your timeline will show everything. Your personal info section will just ignore that event if you post a photograph. Your photo section will basically take that event and then add the photograph in your album, in your mobile upload or something. And so it's the same event, 3 different applications, takes 3 different actions or takes no action. So this is what I'm talking about. Applications can process the same events, but create different views. I'll answer his question. Doesn't event-driven adds a lot of network hops? Actually, I haven't covered that in this particular presentation, but there is an architectural pattern called CQRS, Command Query Responsibility Segregation, CQRS, that basically does that. And what it does is it says that your events can do 2 things. It can either query, or it's a command or it's a query. Query will not modify the system state, it'll just get the data. And a command doesn't have an output, it just is a command that will modify the system state. And then what you do is, from these queries, you create a view, okay? And from that view, you can actually query. So in events where you want to make a query, you create this view and you can query from there. And that's how you avoid a lot of network hops. So that's CQRS for you. CQRS. Just Google this term. There's actually a lot of literature on CQRS. but that kind of solves the problem that you mentioned here. Secondly, isn't there any similarity between event-driven and reactive programming? There is a similarity in the sense that reactive programming, in a way, reacts. Event-driven programming is essentially, I'd say, more of a generalization of a reactive programming, but they are definitely related in the sense that an event happens, you react. So that's the similarity. Now, event-driven goes into much details of what an event is. Reactive doesn't really talk about so much of, okay, what am I reacting to? Whereas event-driven will actually go into details of what an event-driven system is, how do I react, etc., etc. Okay, I should probably add a slide on CQRS. Thanks for the suggestion. The next time I do it. Now, we would talk about how to keep the data consistent, because that's actually a pretty important stuff, right? We know that we have these multiple databases, we have these multiple transactions that are spanning across multiple services. How do we keep everything in track? And this is where the Saga comes in. So what Saga basically is that if you have long-running transactions that span multiple services, then you use compensating actions to handle these failures. So what you have is, in distributed systems, you have partial failure, right? I have a transaction, service A calls service B calls service C, service D service C calls service D, etc., etc. And once a transactions fail, now what happens? I will get into an inconsistency because service A and service B thinks the action is complete, but it's not complete. So what you do is, for every action, you have a reverse and compensating actions or an inverse of that action that you can apply to reverse. For example, so you have a transaction T1, okay? You have a transaction T1 and you have a workflow where T1 calls T2, T3. So you have a transaction T1 that calls T2 calls T3, but it so happens that this failed. So what do? This doesn't happen. This calls the rollback transaction R1. So in this way, what you ensure is one transaction is either complete or it basically is incomplete. There is no such thing as a partial failure, because if you don't have a compensating action, then what you have here is you have T1 is complete, T2, T3 is not complete, but you don't really have any compensating action. So now there is an inconsistency. What R1, the rollback transaction, would do is rollback transaction will basically go back and make the system consistent by inversing the change that T1 did. An example is a bank account, okay? Let's say that I am transferring $100 to you. So what happens? So first of all, the first transaction happens is that $100 is deducted from my account. And then it goes to the second transaction, person's the sender, right? And $100 is deposited to his account and the transaction is complete. It so happens that sender closes his account before the transaction is complete. So $100 is deducted from my account, but doesn't go to the sender. So now the system is kind of in an inconsistent state. So what does it do? It does a rollback transaction. Rollback transaction means, well, I couldn't complete this transaction, so the $100 that I have deducted from your account, I'm going to go back and put that money back. Although you can have edge and border cases. For example, let's say that I close my account also, where will you roll back? So that's where design complexity comes into action. Anyway, so we have talked a little bit about communication patterns, and now we are going to go into details of communication patterns. So when you have these services, you basically have three tiers for these services, right? You have tier one, which are directly customer facing. Then you have tier two, which impacts the customers, but indirectly. And then you have tier three, which has no impact to the customers. An example, say you're using Amazon. Your order placement service is a tier one service. If that service is down, you can't place an order. The system is unusable, period. So it's a direct impact to the customer. Shipment service is a tier two service. If shipment service is down, your shipment is going to be delayed. It's not like things will not work, but it's going to be delayed. Tier three is something like your logging and monitoring. If your logging and monitoring is down, the customer doesn't care, right? For him, he doesn't really care. So these are the three tiers in which you can place your services. And what you do is you use request response pattern, and we'll cover all of these patterns in details, which is a synchronous for tier one, because there was a question earlier that how do services communicate with each other? So this is where that question is being answered, right? And for this, you use an event-driven architecture where you have a message bus where the system would be passing messages on the message bus and the sender receives it. So let's actually look at these two patterns in greater details. Request response pattern, we know that it's a simple REST call. The services would call each other. It's very simple to implement, but the problem here is it's easier to implement and there's a better error control in the sense that if a service is down, you know the service is down, you will get a 404 or some error like that, and you can take response or whatever your response is. The problem is it increases coupling. Each service has to know what is the other service, what is the contract, how do I interact with it. Coupling is okay if you have a small services, but when you have like thousands of services, you don't want coupling. So in a real life system, what happens is the tier one services, let's say you have 1,000 services, typically 700 or 800 of them will be tier two, tier three, and only 100, 200 of them will be basically tier one services. So you will have request response on tier one, which increases the coupling, but it only increases the coupling in a small part of the service. It's also difficult to scale, right? It's difficult to scale because services are aware of each other. So if you want to evolve the system, how do you evolve the system, right? You have to, one service will affect another service. Imagine if you have to change fulfillment services and you have to add a new service between fulfillment and fraud. Not only do you have to add the new service, but the buy service item has to change because it also has to send the data. So scaling can be difficult. The other option is an event-driven option. Event-driven option is an asynchronous option where you have a message broker, right? The order service will put a message on the event bus. This is a typical event-driven architecture. People who are concerned with those messages will just pick up this message. Order service does not have to know how those services basically have to, how those services interact with that message. It doesn't even know who the services is. So that's an advantage, that it's a highly scalable system. It's a very resilient system in the sense that if one service is down, it doesn't affect the order service, right? The messages are queued in the message broker. When the service comes back up, it will start reading the message from where it left. It's very easy to support new scenarios because now you can add and subtract these messages. They just have to connect to the message broker. You don't really actually have to modify the original service. But there are drawbacks. Message broker, now you're introduced another component, which is a highly available component, message broker, which is a highly available component, which if it goes down, you're in really big trouble. Obviously, the more components you introduce, you're more introducing complexity. I think we have a question on Saga, so let me actually get to that. In Saga, what if T1 transaction is successful and then rolled back by the failure of T2 transactions? The changes which had been introduced were already visible for some time and therefore may affect other data which is based on them. That is true, but the goal is that if you have changes that are done by T1, then when that transaction failed, other services take reverse action. So for example, in your cases, let's say that you're saying that changes have been introduced by T1 and which may affect other data. Sure, that'll affect other data. But when T1 is reversed, those changes are reversed on the other parts of the system also. The whole system is designed that when we start reversing, everything gets reversed. The only problem it will create is during that period of time when the reversing is happened, you have a system that is in inconsistent state. But we talked about eventual consistency, right? This is where eventual consistency comes in. So let's say you have another system here, which you can do a rollback, right? During the rollback period, the data is inconsistent, but once all that rollback is consist, the system will come back to its consistency state, and it will be, this is what eventual consistency is all about. API term, and all the related activity like documentation testing is applicable to response. Can API be applicable to event-driven? Generally, no. But generally, API is more used when you're interfacing with an external entity. And generally, the pattern is that your tier 2, tier 3 services do not, in general, interface with external entity. It only tier 1 services introduce. So this is where the communication pattern comes in, is API. If we look at, let's look at the previous slide, API is mostly useful only for tier 1 services. Mostly, although, I mean, it's a term, you can use it for MD, but typically API is not used for event-driven asynchronous pattern. Okay. What if some error happens during rollback? Then you're screwed. Simple answer. The thing is that no system is perfect, right? So you can always have a edge case where things fail. For example, your databases, right? You're replicating your databases for basically resilience. What if all the replications fail? What happens? Well, then you're screwed. That's what happens, right? So there is an edge case where all the systems, all the relevant systems fail, things you'll get into trouble. But the key idea is that that would not happen frequently. So if you have 3 replicas of a database, the probability that all 3 of them fail is going to be small, not 0, but very small. The probability that one is going to fail is high. So there, what you're adding by, you're basically increasing the resiliency of system by adding more replicas. But if all 3 of them fail, then there is not much you can do. You can obviously have a backup in some cold storage, sure, but then your cold storage can fail and then that loop can go infinite. So there have been cases. For example, I think there was a famous case of GitLab where they basically stored all the data and they have 5 backups. It turns out all 5 backups failed. So basically, people lost the data, period. There was nothing much they can do. Is there any backup for queue messages? Your message broker typically has a backup for queue messages because it knows what message was delivered to what service. So that backing up is done there. You also have logging and auditing mechanism. So there's a logging mechanism that is continuously feeding logs. So let's say for whatever reason, message broker could not back up, maybe because message queue is full, right? You want to then fix, okay, I missed this message. You can always refer to your logs. Again, it comes back to, you don't have infinite resources. So you can always add more redundancies that will reduce the probability of failure to smaller and smaller and smaller and smaller. You still won't make it 0. In an edge case, you will have a problem. But generally, you have systems that will take care of message backing of queues for messages. Are there any products or library out there that has events roll back to a particular time in history, an optional replay? Can this be done with general purpose? No, I don't think so. And I don't think it's even possible. The reason is that this is a very problem specific thing. Like what is a rollback? Rollback depends on your problem. Like in a bank transaction, you have a rollback. So you can't have a general purpose system that can roll back, right? This is something that is very much tied to your application logic. You have rollback transactions in the sense that with databases, if you make a SQL query and write, you have a rollback transaction in the sense you can delete what you wrote. So primitives are given to you by systems. But exactly rolling back an entire transaction is a very problem specific. So that is something that you would have to implement. Okay. Okay, so we have covered this part. Now let's go further. Asynchronous workflows. Okay, so this is a good example of about async. There are initiatives to standardize async API, but it is less mainstream compared to. Oh, actually, I wasn't aware of it, but thank you for your reference. I hope it happens. The thing is, async API, yeah, that would be something good. Thanks for the info. Anyway, so asynchronous workflow. So we talked about how the services interacted. So this is an example where you have this user interface and you have a tier 1 service and you have tier 2 service. So what happens here is that tier 1 service receives it via request response, okay, and then acknowledges back to the client, and then sends a message to the message broker or async. I'm just using the term async. I'm not specifying how it's sent. It could be via message broker or make async solve to a tier 2 service. And what this does is add scalability. So you can have this message reply, so customer immediately gets replied, order placed, period. And order ID, I have placed your order successfully. And the product service will go and process something in the background whenever it happens. Thanks for CQRS. Is there something that is something I was looking for? Is there any documentation on design patterns for distributed services like GOF pattern? I don't know what GOF pattern is. Could you elaborate what GOF pattern is? There is obviously a lot of documentation for CQRS. There's a guy named Martin Fowler who writes a lot of articles. I have covered CQRS in my another presentation. So what I'm going to do is I'm going to pause and bring those slides and talk about CQRS. But yeah, Microservice IO is actually Chris Richardson has this website. This website basically is, I've talked about this reference. So let me actually get to that site. Let's actually talk. Oh, okay, this one. So this microservice.io basically is same as this guy, microservice pattern. This actually talks about this microservice patterns. This actually talks about a lot. And microservice IO is actually written by the same author. So a lot of what is written in Microservice IO is all covered in details in this book. This book is an excellent read if you want to implement microservices. And I think he has a framework also called Eventuate or something that actually talks about it. GOF, Gang of Four, design patterns, elements of this one. For patterns or distributed services, I'm not aware of any documentation, but hey, Google helps. I don't know if these design patterns that they have, I'm not sure if they are really that much applicable to services, because I think this is more of a generalized. I've used some of these design patterns, but I'm not aware of any documentation. But I think if you Google, you might be able to find one, but I'm not aware of any. Okay. So we've talked about asynchronous workflows. Okay, I think there was a question about testing microservices. So let's actually go back to testing microservices. Pure services. So pure services, the behavior is very predictable, right? You don't have any IO, so you can test it exhaustively. The only problem that happens is when you have to test the ones that have persistent state. So impure services, they are unpredictable depending on external state, because you can't really model the external database. So you can create stubs and you can have mock test data. So usually what people will do is the production data, they will replicate this production data. They will strip off user identification for privacy reasons and create a mock data. At Facebook also, they had the same thing. We have internally fake users whose data somewhat resembles the real data, but the identities are all kept secret. And then we can test anything using these so-called non-existent fake data. So you can use that. So you'll have certain services. Some people even like when the messages are coming, they will bifurcate and they will have one stream going to the production system, one stream going to the test system. And then test system would basically have all the data that can be used. Certain services cannot be tested exhaustively in the sense payment gateway, right? I mean, you can test some aspects, but if you test it exhaustively, you are incurring a payment, right? You can maybe pay 1 cent, 1 cent, 1 cent. Testing services, event-driven. Well, this is the original architecture. What you can do here is you can have a test setup where you're injecting test drivers and test interpreters. So you can actually put some test drivers and test interpreters and then test how the service would behave. There are payment sandboxes to solve that problem. Thank you so much. I wasn't aware of that. So great. I'll add that to the slides. This is the great. When people tell me more information I don't know, then I can keep updating my slides. But anyway. Okay. So reads messages from the event bus and then injects messages into this one. Now, one of the big advantages of using functional programming is that when you have mostly pure functions, you can actually very easily analyze and reason about. And so static analysis is very good and effective to detect issues in functional programming. And an example we used in one of the startups which used F#, where all of this work that I actually did was applied, is that we had a set of NT patterns, and then we will parse the code into a AST and detect these NT patterns. And in context of F#, there is actually F# compiler services that provides you all the AST definitions and parsers. So parsing the code is pretty easy. And then from there, you can just detect the NT patterns very easily. Scalability. Okay. So one of our goals is scalability. And, one of the big advantages that functional programming gives you is that it has infinite scalability, massive parallelism out of the box, because you don't have states, right? So you can when you have pure services, you can have pretty much replicas as many as possible. You don't really, with immutability, you don't really have to worry about a lot of mutex, block, and race condition. Now, this is more specifically applicable to functional programming, right? So if you're using Golang or others to implement the services, some of it would not be applicable, although I believe that Golang has very good primitives for parallelism. So it allows you to scale. So Jet.com was using F# and they scaled very easily from few thousands to few millions. So that's a big advantage that functional programming has for scalability. Productivity, of course. Functional code is much more concise than its corresponding object-oriented code. So means you have to write less lines of code. Code is a liability, it's not an asset. So the less lines of code you write, the more productive the dev is, the more functionality you can deliver, the less the chances of bugs are, because less code equal to less bugs, right? Functional programming languages are basically declarative languages. They are very concise. You can read the code and you know what is happening. They're very clear. So that means low maintenance cost. You get a lot of productivity benefits with functional programming. Simpler code. So the code is very simple because code is more like, it's a declarative code. You don't describe this algorithm in details, you just describe the problem. So it's very easy for new people to understand. So productivity is a big benefit. Then you also have code correctness, right? It has a very good type system like F# or Scala. So strict typing will make the coding easy. Immutability will make code a lot more predictable, understandably. And then you have pattern matching. So you know that for this particular case, I have to take this action. Scala has case classes, F# has discriminated unions. So a lot of these errors that you forgot some case, forgot something, it gets trapped in compile time. Because if you forgot to take care of a use case, well, compiler will catch it immediately. And type system, fantastic type system will make illegal states unrepresentable. A case study that we had with Twitter used Scala. It started as a Ruby and Rail and moved to Scala. There's an article on Redfin what benefits Twitter had with Scala. And Scala is one of the dominant languages, or it used to be dominant language. I think since Elon Musk came, a lot of changes have happened. I do not know what's happening in Twitter, and I don't think anybody else knows what's happening in Twitter anyway. So to summarize, functional programming is a great paradigm, which is very good for modeling web services. Okay. We know that microservice architecture has a big benefit of faster innovation. We can model events using algebraic data types, F#'s distributed unions, Scala's case classes. Keep the service pure for scalability, because if the service is pure, then you can scale it very well. Scalability is important for highly available, highly distributed systems. Functional programming gives you benefits of scalability, productivity, and code correctness. We saw the details of all of that. And finally, questions. But before questions, there's something that I wanted to point out. And what I want to point out is that on my web page, I will share the link with Diana later on with my web page. Oops, sorry. With my web page, I actually have these. Oh, why are the slides not working? Oops, sorry. These slides are actually available here. So these, not exactly this version, but the slides are available. I think I changed. I have probably changed something in certain URLs. Let me look at it. Sorry. I have changed the names. Microservices in FP and microservices, or I'll actually make, okay, underscore, not. These particular slides are available here. Slides here are usually a little more detailed than the ones I presented, but mostly will have the same context, right? Another slides that I point out. So this is about microservices and functional programming. Now, if you're interested in microservices in general, nothing to do with functional programming, those slides are actually here. So these are the slides from basically microservices and event-driven microservices in context. So there's nothing to do with functional programming. And I know there was some questions about CQRS. So I think I have talked about CQRS here also somewhere. I have to find out where I've talked about CQRS, but I'm fairly confident I would have talked about CQRS. There you go. Yeah, so this is the CQRS. Wonderful. So this is CQRS pattern, command query responsibility segregation, right? So if you're interested in microservices without like nothing to do with functional programming languages, this link, which let me actually post it here so others can download. And I usually keep, like, I add more information from time to time. So let me just this one and this one. Yeah.
People are saying that they can see just PowerPoint right now and no SQRS slides.
Ah, okay. Okay. So what I can do is I think, hold on. I think when I'm sharing the system, I'm probably not sharing my entire screen. Okay,
Yes.
that's because I'm not sharing my entire screen. That's probably. So why don't I do this? Share my desktop. Okay. So share my desktop. So now I have posted these links. Okay. These links are actually from my other talk and they cover CQRS. So this is the CQRS pattern. So what you have is you have the write, which is a command, and you have the read, and this is the database, and then you have the command model, and then you have a query model. So query model is actually kind of built. Okay, and then you can query from there because you can't query events, right? And CQRS has its own benefit. I'll probably add that in the main slides. It's much needed for event sourcing. It improves the separation of concern because now you have read and write different. It supports multiple denormalized views because you can have multiple read views, right? But obviously there are drawbacks in the sense that there is a complexity. There's some code duplication because now you have multiple views. So there's some code complexity, duplication there. And also our system is not strictly consistent because if there's a command that will change that event will go to the database. Ultimately, the query model will read it, update its model. So it takes time. Time is very short, but still it's not a strict consistency. So that's the thing. And I think Scala rollback I've kind of covered. So this was the example I actually gave for basically the credit service where you can close the amount and compensation. And one of the things that Scala has is that Scala does not have, Sagas does not have isolation. So you have the ACD, but you don't really have I. Okay. Another aspect that I probably should cover is how do you make decision making in Scala. So you have two aspects of that. One is choreography, which is a distributed decision making. So it's simple when event sourcing, but it increases coupling among components. And then there's another one where you have orchestration, which is more of a centralized. People can see the slide, right?
Yes, now we can see decision making in Sagas.
Yeah. Good. And then you have orchestration, which is more centralized logic, which I feel is much better because it's much easier to understand. And then, yeah, okay. So here, what I'm actually going to do is I can go back and share the slides because this is, so the links, so wonderful. So now I am up for questions. And what I'm actually going to do is I just want to go back and see if there are any questions that are unanswered. So I just want to make sure all the questions are answered. We have talked about the main disadvantages of microservices. We have talked about communication. We have talked about when not to use, how do you deal with complexity. We have talked about consistency. Instruments of communication, presentation. Okay, so testing, we have talked about testing. You can do smoke testing and integration testing. Okay, let's expand a little bit on smoke testing and integration testing. Um, Depending on if you have a request response, then typically you have drivers and stubs. So you can take a subsystem out and then use them as integration testing. Smoke testing also you can do by having, like, typically what organizations have is they have like a pre-production or a staging environment, which is somewhat of a replica of production environment where all the services are doing. So you can do integration test and smoke test there. We have talked about good microservices. We have talked about databases, independent services, Erlang, microservice architecture, moving parts, synchronized data. We have talked about that. Practical examples, how do you caching? We have talked about that. We have talked doesn't event added, Saga. We have talked about API term, error during rollback, message queues, CQRS. We have talked about it. Gang of Four, I can Google, but I'm sure you can Google and find out. I'm not aware of any particular reference to it. Do you recommend any books for functional programming? I think it depends on the language that you want to learn. For F#, I think the book that I love the most, let me actually again switch. I can probably switch my desktop. I don't know, it might just be better for me to switch to desktop. Okay, so let me actually end this one and we'll go back to this. So for F#, UHPAUI, silly. Okay, for F#, I think Don Syme, who's the creator of F#, he has excellent books, Expert F#. If you want to read Scala, my favorite book is Scala for Impatient. And because the good thing about this book is its book is brief. You know, it assumes that you know programming, and then you can just read basically the important concepts. So I see that there is a new edition, Scala for Impatient, excellent book to learn Scala. For Haskell, I'm not aware of any. I think Haskell for Real World, that's a good reference for Haskell. Okay, sorry, CQRS slides. Okay, can functional programming be applied, for examples, with Java and some library? Java supports a lot of functional programming concepts like Lambda functions, etc. Java has it. So yes, you can do that. Okay. It's not designed to be a functional programming languages. It's just like functional programming concepts are add-on. C# on the other hand actually is pretty good. You can do a lot of functional programming in C#. But I think Kotlin is pretty good. In fact, I generally do not recommend people using Java because I think Kotlin is way better than Java in practically everything. I think I've shared the CQRS, I've shared the links. Saga is so it's covered by SCAP theorem. Pay attention that C and A are there, but not the same as this one. Okay. Orchestration can be a single point of failure in Saga. Yes, orchestration can be a single point of failure in Saga, but then also because you have use cases. So again, it's a kind of compromise, right? You can create certain services that are more highly reliable and have replicated. The thing with distribution decision making is it's a headache to understand the system, especially when you have 1,000 services, you'll just go nuts understanding. So that's the reason why orchestration is good. What is a good pattern for organizing source code for multiple microservices, potentially using some common function? Can all microservices be compiled as a single unit, or this is an anti-pattern? See, the thing is that you can compile microservices as a single unit, but what benefit would you get? Because you don't really have atomicity of deployment. So even if you compile it as a single unit, yes, it's not an anti-pattern, it's just something that wouldn't really give you any benefit. Good pattern. If you have a mono repo, then that's easy because you can have like microservices in some separate folders, common code in separate folders. Otherwise, you have Git repositories with common code in one repository. I think Git supports like multiple, you can do, I think Git can, I'm not super familiar with Git because we don't use a lot of Git, but I think you can reference other repositories from Git also. Otherwise, you in your CI/CD pipeline, you have multi-repo checkout. So you can actually do that and have common parts in a separate repo and microservices in a separate repo. What is the maximum number of microservices should I have before choosing another architecture to keep balance between this one and this one? This is very problem dependent. Generally, there is no such thing as a maximum number. It depends on the size of your organization, etc. I don't know. Typically, organizations have few hundreds to maybe 1,000. I think more than 1,000 is a little bit too much. But again, you should not think about microservices in terms of I should have this many numbers of microservices. That's a wrong way of thinking. You understand why microservices are useful. So you have services where you need them to be separate. You need them to be separate because different teams are going to be working for them, because they need independent releasability, they need better scaling properties. That's the reason. And then depending on the problem, that number is going to be decided by that. Books for functional programming in Java. I'm not aware of a particular book, but I think if you search on Amazon, there should be plenty. Questions about boundary between functional and non-functional. We can follow all the principles, stateless, pure, etc. DD. We just use non-functional languages like Java. We get most of the advantages in this presentation, but without FP. It feels to me FP is an implementation detail orthogonal. Yes. So that's a good question. So here's the thing. Functional programming is a style. A functional programming language is basically a language that facilitates those styles, right? You can do functional programming in C#. I do a lot of functional programming now in C# because all the functional programming constructs that are there are available in C#. So you can get all the benefits of functional programming in quote-unquote non-functional language like Java. I wouldn't really call it Java as a non-functional because it has Lambda functions. It has a lot of functional programming constructs, right? I think you're confusing between the language and the style. What I'm saying is functional programming, maybe I should be more clear. Paradigm is a good way to model services, right? You can do it using an object-oriented programming. Yes, most of the languages are hybrid anyway. In F#, I can have a class hierarchy and I can do full object-oriented programming. The same thing is true for Scala. It feels to me that is orthogonal. Yeah. So there is an event-driven systems. That's a distributed systems theory, right? That you're talking about. That's one thing. And then how you implement it is a second question. And this is the reason why I have two separate presentations. So I had two different slides, one that talks strictly about architecture, nothing to do with functional programming. Functional programming is more on the implementation detail of it. So I'll agree with you. Do you have a complete code example implementing best practices that you have it? I have it, but I don't think I can make it public because it's a proprietary code. I'm so sorry for it. But if you read those literature, you would have a lot of examples there that would kind of give you good examples. For example, Microservices Patterns is an excellent book. It has all the examples. I think they use Java for it, but they have really good code examples there. What do you think are the best triggers that show tech team that they need to change from monolith to microservices? I think if the team has the problems that monolith basically has, they would know it on their own. For example, if they are finding that they are wasting too much of time waiting for each other, then that's one good trigger. If they think that their test cycles are too slow, right, because monolith doesn't scale, that's the second trigger. Essentially, you don't change from microservice to monolith because monolith to microservice because microservices is cool, right? That's not a good reason to change. You change because you have a problem that your existing architecture cannot solve it. So if the team realizes that we are running into problems with this architecture, we need to change, then you don't really have to convince them. And if you're not running into fine, then why the hell would you want to change to microservices, right? Don't fix something that isn't broken. Any other question? Thank you. Okay, do we have any other question? Otherwise, my contact information is there on the slides. So please feel free to ping me anytime. Usually what I do is I basically keep updating the content. So what you'll have on the link is going to be mostly more latest as opposed to one that I've just presented. Merge from microservice to monolith. Do you have a Yes, so there has been cases where people felt that it was better to go from microservice to monolith. I think that the very famous Amazon case study for Amazon Prime. And I think to me that happens when people just, they have a tendency, oh, microservice is a cool new technology, let's just use it. And they just use the technology just for the sake of using a technology. They don't actually understand why they are using it, right? There's nothing wrong with having a monolith. It's not an anti-pattern. It solves certain problem and it doesn't solve certain problems. So if you are facing the problem monolith doesn't solve, then you're going from microservices, right? Now, if you have gone to microservice just for the sake of it, and then you realize microservice is a headache, you obviously would want to come back to monolith. Any patterns for properties config management? I don't think there is any kind of property, and I think properties are a little bit implementation and language specific thing. So I don't know if I can give you any advice for it. Config management, you have the standard config management tools that store, like AWS has feature, they have config management tools that store feature flags, and I think Console, Nomad, HashiCorp has some products like Console, etc. They have these console. Now, when you're talking about config management properties, right, there are two kinds of properties. There's a static and there's a dynamic, right? Static means it's baked in the compile time. So it's somehow stored in your repository. And then dynamic is the one that you basically would be changing it during runtime, for which you'll have to use a system like Console or some AWS service for storing feature flag. I'm sure GCP and Azure would have something similar. Where can I find research papers for programming? I think you can find everything on Google. What happened in the world that microservices become so popular? Two things. A, systems were getting bigger and bigger, and obviously monoliths don't scale. So microservices came in, and suddenly it was a solution that solves all these scalability problems, right? Scalability always has been challenged. So that's reason number one. Reason number two, which is true for a lot of cases, is the hype cycle, right? Every time a new technology comes, people get excited. Yay, there's a new technology. So there is obviously a lot of hype around microservices. Everybody hopped on to microservices just for the sake of it, and some of them realized that we made a mistake, maybe we shouldn't have, but that's another issue, right? So this is why the recommended approach is that every new technology, you understand the pros and cons. What are the problems that it is solving, and what are the problems that it is creating? Because it's going to create another set of problems. Then you make a decision. Is this something that you want to use? Don't just hop on to microservice because, hey, it's a cool new thing, let's just use it. That's not a good reason to do that. Okay, thank you. Any more questions? Otherwise, as I said, there are links. Please feel free to download the questions. Please feel free to ping me anytime you want. I would basically update the presentation from time to time. So you basically can check periodically and you'll have the latest content on those links.